Let's get one thing straight. A computer isn't magic. It's a machine. A wonderfully complex, ridiculously fast machine, but a machine nonetheless. The best way to understand any machine is to think of it as a workshop. Imagine a perfectly organized workshop, filled with tools, benches, and blueprints. Tools, benches, blueprints. Every single piece has a specific job, and they all have to work together to build something amazing. Your computer is just like that. It has a place to do the work, a place to store tools and materials, and a set of instructions, the blueprints that tell it exactly what to build. When all those parts hum along in perfect harmony, you get to browse the web, play a game, write an email. But when one part gets stuck or has the wrong instructions, the whole project grinds to a halt. So why should you care about what's going on inside that box? Because understanding the basics is a superpower. It demystifies the technology you use every single day. It helps you troubleshoot problems instead of just getting frustrated. When your computer slows down, you'll have a hunch about whether it's a cluttered workbench or a full warehouse. Cluttered workbench. Full warehouse. Knowing how things work is the first step to making them work for you, not the other way around. It's the difference between being a user and being a builder. We're not going to get bogged down in mind-numbing jargon. We're going to stick to the core ideas, the fundamentals that make the whole thing tick. We're taking a peek under the hood to see the engine. This workshop analogy is our home base. We're going to keep coming back to it. Every new concept, from the processor to the software, will have a place in our workshop. Welcome to the workshop. The tour starts now, and we're going to build an understanding from the ground up. Alright, let's start with the tangible bits. The hardware. In our workshop analogy, this is everything you can physically point to. The building itself, the power outlets, the tools, the benches. In computer terms, hardware includes the case, plastic or metal, the screen, the keyboard, the mouse, and all the chips and wires tucked away inside. It's the collection of physical components that form the computer's body, the parts that move electrons. Without hardware, software would just be a bunch of ideas with nowhere to go. The key pieces of hardware each have a specific, crucial role. Input devices like a keyboard, mouse, mic, camera. Output devices like a monitor, speakers, printer. Inside the case, the motherboard, the workshop floor, and the power supply, the electrical panel. The processor does the work. Fans keep it cool. They communicate over electronic pathways called buses, hallways and conveyor belts moving information. Buses carry data from storage to the workbench and send finished work to the display. Wider, faster buses move more in less time. Hardware is an interconnected system, not a random pile of parts. Now for the other half of the equation, software. If hardware is the physical workshop, software is the intelligence, the blueprints, schematics, instruction manuals, to-do lists. It's the ghost in the machine that tells the hardware what to do, how to do it, and when. An operating system is the master blueprint for the entire workshop. Windows, Mac OS, Linux. It manages the tools, coordinates tasks, and decides who gets the workbench and when. The shop foreman. Applications are specific project blueprints. A web browser, a video game, a word processor. When you open an application, you're handing a new blueprint to the foreman. Build this now. Software is written by humans in programming languages, then translated by compilers or interpreters into on or off commands the hardware understands. Software provides the logic. Hardware provides the action. One is useless without the other. A perfect blueprint with no tools builds nothing, and tools without a plan do nothing. The plan and the tools working in perfect sync create powerful, versatile machines. At the heart of our workshop is a special, hyper-efficient workbench, the CPU, the central processing unit. The CPU is the master craftsman, the lead engineer, the brain of the operation. It doesn't store blueprints or raw materials, but it reads instructions and performs the actions. It does the math, makes decisions, and directs other parts of the workshop. From opening a file to calculating a spreadsheet, the CPU executes the core commands. It's the ultimate doer. A simple, relentless cycle. Fetch, decode, execute. First, fetch an instruction from its temporary workspace. Second, decode it. Add, move, or compare. Third, execute it using arithmetic and logic circuits. Then immediately start again. Clock speed, in gigahertz, is like a metronome. At 3 GHz, it ticks 3 billion times per second. Modern CPUs have multiple cores. Several craftsmen working in parallel. The CPU constantly talks to memory, graphics, and storage across buses. Inside are billions of microscopic switches, transistors, where computation happens, one tiny, lightning-fast step at a time. Every good workshop needs two kinds of places, a workbench for now, a warehouse for later. Memory, or RAM, is your main workbench, a super-fast workspace right next to the CPU. Opening a program brings a copy from the warehouse to the bench. RAM is volatile. When power stops, it forgets. So you save your work back to storage. More RAM means a bigger bench. Too many projects and it slows down shuffling. Storage is the warehouse, non-volatile, long-term, your OS, apps, files, photos, documents. Two main types, HDD with spinning platters and SSD with flash, like a robotic retrieval system, much faster. On startup, the OS loads from storage into RAM. Clicking an app fetches its blueprint to the bench for the CPU. It's a trade-off. RAM is super fast but costly and temporary. Storage is slower but cheaper and permanent. A good system balances a big enough workbench with a large enough warehouse for the future. How can simple electronic switches perform tasks as complex as editing video or searching the internet? Binary. Computers think in on and off, 1 for on, 0 for off. Every letter, pixel and note becomes a long string of ones and zeros. Enter logic gates, tiny circuits that make decisions on binary inputs. AND is like a door with two keys, both must turn. Or opens if either handle is pushed, NOT flips the state. Like Lego, simple gates combine into adders, then into circuits that add long numbers, multiply, divide, and more. Every CPU calculation is millions of gates flipping at incredible speeds. Hierarchy. Transistors make gates. Gates form modules like adders and memory cells. Billions of modules make a CPU. The computer isn't smart like a human, it's a machine following simple rules, very fast, in a language of ones and zeros. Computers are incredibly complex. If everyone had to know every detail, nothing would get built. The solution is abstraction, layering. Like a skyscraper, experts focus on their layer and interfaces. At the bottom, electrons in silicon. Above, transistors, then logic gates, then microarchitecture building CPUs and components. Each layer hides the complexity below. CPU designers think in gates and data paths, not electrons. Moving up, the operating system abstracts hardware, offering simple commands like subtitles. Regardless of SSD or HDD, write one program. The OS makes it run on many hardware configurations. At the top, you interact with applications. Developers think in buttons and menus, not clock cycles. They build on all lower layers, trusting OS, hardware designers, and physicists. Layering lets small teams create powerful software. Let's trace a simple action through our workshop. You move your mouse to the calculator and click. The input device sends signals, horizontal, vertical movement, and a left button press. At the receiving dock, the OS, our foreman, understands the event and sees you click the calculator. The blueprint lives in storage. The OS finds it and loads it over the bus into RAM, the workbench. The OS cues the CPU, start here. The CPU fetches, decodes, and executes. Compute shape, color, positions. It sends the info to the GPU, which renders and sends pixels to the monitor. From physical click to pixels lighting up. Input devices, the OS, storage, RAM, the CPU, the GPU, and output devices all work in perfect coordination. Our workshop is powerful, but it's not invincible. Things can go wrong. Safety starts with power. Surges can fry delicate tools. A surge protector is cheap insurance. A UPS buys time to save and shut down safely. In billions of ops per second, rare errors happen. Error-checking codes add bits to detect and often correct flips, like a built-in proofreader. Connecting to the internet opens the doors to collaboration and to saboteurs. Good hygiene matters, strong passwords, updates, and caution with downloads. Lock your doors, install alarms, vet your visitors. Every design is a trade-off. You can't have fastest, cheapest, smallest, and most efficient all at once. A gaming rig trades size, cost, and power draw for performance. A thin laptop trades raw power for portability and battery life. Understanding trade-offs helps you make informed choices. Ask what the engineers prioritized and why. It's all part of the grand, beautiful compromise of engineering. By the end of this, you won't look at your laptop or phone the same. You'll see a bustling workshop executing billions of tiny steps every second. You'll see the elegance in the design and the sheer cleverness of it all. So, grab your safety glasses, metaphorically, and let's get our hands dirty. Welcome to the workshop. The more you understand the fundamentals, the more the whole system works for you, from the ground up.